Now, this is a very interesting circuit, and it was actually suggested by a person from Woodhaven, New York. This shows how the fan blade can actually store energy. When I place the fan on the motor and I push and hold down the press switch for a few seconds and then release it, the LED flashes. Why is that? The mechanical energy stored in the fan blade causes the motor to act like a generator. And when the press switch is released, this energy will create a brief current that will run through the LED. It's extremely brief, but it shows how a motor can store mechanical energy. However, without the fan, although it works in this case, the motor may not have enough energy to power the LED. Now you may wonder, what's the point of the antenna in this circuit? Well, actually, the magnetic coil within the antenna can produce energy just like the motor and fan blade. When I release the press switch after holding it down for several seconds, the red LED flashes because the magnetic coil within the antenna acts like mechanical momentum, and energy stored in the magnetic fields of coils used to be called electrical momentum in the early days of electronics. And you may better understand how magnetic fields produce electricity in the following project. In the previous project, I explained how a magnetic coil, which was inside the antenna in the previous project, can produce electrical energy. Well, this is the first project to use the electromagnet, and when I turn on the slide switch, nothing happens. But when I turn it off, the LED will flash. That's because the electromagnet actually stores energy from the batteries inside a magnetic field. And then when I turn the switch off, the magnetic field will collapse, causing the energy to flow through the LED, even though it's extremely brief. This project is similar to 530, which was the antenna storing energy project, but except now we're using the transformer. This is another suggested project, actually from the same guy from Woodhaven, New York. When I hold down the press switch and then release it, the LED flashes because there are coils within the transformer that contain magnetic fields which store energy, and releasing the press switch will create a brief current through the LED. We are going to use the relay. The relay has a coil similar to the one in the transformer that stores electrical energy the same way. Releasing the press switch will send a current through the LED. This circuit will show you how the transformer works. When I push the press switch, the red LED blinks, and of course the lamp comes on. But when I release the press switch, the green LED flashes. I'll do it again. The reason why the red LED flashes when I push the press switch and the green one when I release it is because the current from the battery charges the magnetic field within the transformer, and that will stay constant as the press switch is held down. But charging the magnetic field will power the red LED, then releasing the press switch will remove the magnetic field, which will in turn produce a similar current through the green LED. It's complicated, but here they show you how the transformer works. It's pretty interesting. This is a machine siren. This project shows how a magnet can affect sound. When I turn on the slide switch, you hear siren, but sounds distorted. Now, when I push the press switch, you're supposed to hear a clear siren, but you don't for some reason. However, I can explain how the circuit works. The magnet distorts the sound from the alarm integrated circuit, but pushing the press switch includes the C2 capacitor, which in turn bypasses the magnet and improves the sound quality. Now, I have done this circuit, built this circuit on my own. However, it was suggested by a guy from Alberta, Canada. But this circuit allows you to actually hear the motor. Listen to it as it spins. Can you hear sound coming from it? The reason why you hear the motor is because it uses magnetism to convert electrical energy into mechanical energy, and as the shaft spins, it connects and disconnects several sets of electrical contacts in order to give the best magnetic properties. And as these contacts are switched, an electrical disturbance is created, and the speaker converts this into sound. So I shouldn't really say that the motor itself sounds, but it produces an electrical current that will make the speaker sound. The following two projects will talk about a complicated force, which is called back electromotive force, or back EMF. This is a force that is generated when the motor spins. It could be thought of as the motor's electrical resistance. Then there's the front motor's force, the front electromotive force, which is exerted as the motor spins the shaft. And this circuit will demonstrate how the back EMF increases and the current decreases as the motor speeds up. With the fan on the motor, the back EMF is low, but the current is high. That's why the lamp glows brightly. But I'm now going to take the fan off the motor and turn the motor back on. Now the lamp is much dimmer than it was previously. Right now the back EMF is high and the current is low. For the variant of back EMF, I'm going to turn on the slide switch, and the 6-volt lamp, or the L2, is going to be bright at first. Then it does become a little dimmer. It might be hard to notice, but it dims as the motor speeds up. Then I'm going to cover the photoresistor, and the motor slows down a bit. You could just place the photoresistor over the lamp to get the fan running at full speed, but since I'm outside, I don't have to do that. The Q2 transistor will try to keep the motor at a constant speed despite the EMF due to light on the photoresistor. This is another oscillator circuit that makes sound. When I turn on the slide switch, you hear a fairly high-pitched sound. Then when I push the press switch, the frequency becomes lower because I added the C2 capacitor. Releasing the press switch will disconnect it. Then I can replace the C2 capacitor with the C3 one to make the sound pitch even lower. This is a lighthouse. When I turn on the slide switch, the red LED will flash, just like the light of an actual lighthouse. And a lighthouse uses a very bright light to let ships know where the coastline and other potential dangers are, so that they avoid a collision. This is a circuit that I've looked very forward to demonstrating, and that is Diode Wonderland. I'm going to cover the solar cell and turn on the light switch, and the LEDs should not light. But when I allow light to hit the solar cell, the red LED comes on, and although very faint, so does the green LED. Also, one segment on the display lights. When I hold down the press switch, although it's very faint, all but the middle segment of the 7-segment display light up. And this circuit is called Diode Wonderland because it uses so many diodes in the circuit, including the non-illuminating D3 diode. Cover the solar cell and all the LEDs go out. This circuit will allow you to see the difference between the low and high current meter ranges. Using the low setting first, the slide switch will stay off, and I'm going to keep the L1 lamp, which I will later include in this circuit, disconnected. The meter reads about 1. Now, results may vary depending on the quality of your batteries, but I am going to place the lamp in the circuit and the meter will read close to 10. Now I am going to change the meter setting to high and turn on the slide switch. And now the meter should read just above 0. Finally, I'm going to push the press switch and the meter will read about 6 because the speaker only has about 8 ohms of resistance, so you can tell the difference in resistance of the different components. You know, you can do different combinations. The following 3 circuits will allow you to measure the current of different components. First, we're going to start with the motor and fan. I'm going to place the fan on the motor. And then the meter is set to the high position. When I push the press switch, the meter deflects to around 6. And that's pretty high because turning the fan requires a lot of energy for the motor. Now I'm going to remove the fan and hold down the press switch again. The meter reads a lot lower because the motor does not require as much energy to spin when the fan is not included. The meter now reads about 3. I replaced the motor with the 3-volt lamp. Now, the manual says 2-volt lamp, but the particular lamps that I have, which are built into the component, the L1 lamp is 3 volts. But I'm going to hold down the press switch, and the lamp is fairly bright, and the meter reads around 5. Almost 5. And then I am going to replace the 3-volt lamp with the 6-volt lamp. Now, the lamp is not as bright, but the meter reading is about the same. 5, it registers, well actually now it's dropping to 4. But you can compare the meter readings and brightness of both lamps. This circuit combines those of projects 545 and 546, the previous 2 projects of the previous 2 projects. And when I turn on the slide switch, the meter set too high will measure the current of both lamps, and it's around 5. But when I push the press switch, the 3-volt lamp is bypassed, and now it measures the current of the 6-volt lamp.